Hi everyone, again. Today I'm here to talk about using graph theory to model a production line and predict delivery dates. I hope that at the end of this talk, you start to think differently regarding small production line factories and how graph theory can help them to be one step ahead in the competition. Um, just a quick heads up. So, who am I? My name is José Viana, as we introduced, but everyone calls me Zé Diogo, and I'm a backend engineer at Remote. Remote makes running global teams simple, HRIS, payroll, international employment, and more. So, if you are planning to hire globally, be sure to check them out. You can also follow me on Twitter with the following handles: Zé Diogo Viana, or check out my personal website to know more about side projects or blog posts I wrote. So a small overview of what we are going to talk about. First, we're going to highlight the problem, then go through the visual representation of it, and also possible Neo4j representation, a little bit into queuing theory, and then we're going to go on the second part and predicting delivery dates, also using graph theory. And at the end, a small comparison against AI or machine learning, and a quick a case study just to show. So the problem, to help you all understand the problem statement for what I'm talking about today, I decided to choose a carpentry. As an engineer, I like to think that I build things, some digital, some physical, some work, some don't. So therefore, the carpentry workshop as my example, because carpenters build things. And yeah, now let's imagine this carpentry where we have the following workstations. Each one is responsible for a specific production part. For example, in a carpentry, we can have the cut wood, polish, paint, varnish, the assembly. Each of these sections is separate from the other, but they all together only complete the workshop. So continuing on the problem, our carpentry is not big enough to, or let's suppose our carpentry is not big enough to mass produce items in an assembly line. For example, it still depends on manual processes because it just doesn't have the scale, or it's not big enough to have automated tracking mechanisms through robots or machines because, as you know, in some production lines, the big ones already have machines that control everything. But however, our carpentry is big enough to receive lots of different orders for our scale again, and also could benefit from production line optimization. The question is, how can we optimize our production line if we don't have that much data? This is a very common situation where lots of factories don't have the scale to invest in automation and technological improvements through those robots and machines, and still rely on manual processes. These, as it's natural, are inefficient or poorly organized most of the times, and could benefit from a simple and automatic analysis of their production lines. So that's what we're going to look at today. Oops, sorry. Here's a small visual representation. So this is already a sneak peek of what we're going to see ahead. Not all orders have the same processing. For example, looking at the image, we see the path that the red, green, yellow, and orange orders will do inside the production line. So for example, the green one will go through station 3 and then 4 and end at 5. Imagine these 3 as a polish, 4 varnish, and then the 5 is the assembly. A chair may not need a painting or a protective coating, but a kitchen table might. So these are the difference, and we can think of this as a unique line that starts in the same place and ends always at the same place. Every order can have a different path. Also, you can see that this is already being built as directed graph, and a given workstation can receive orders from various others. For example, our example in 5 here. This graph can also have cycles where workstations get repeated along the way for the same order, but the full delineated path, for example, as we have down here, should have a single start and an end, so it shouldn't have an endless cycle. We can build this knowledge graph by simply enabling employees to interact with the start and stop button, where we pass like the order ID and the respective workstation. Imagine something very similar in the factory. And something as simple as this should be enough to give a great start to collect data for our small carpentry and move it one step ahead of the competition. Let's see how. So here's a small possible Neo4j representation. This is a very simple one where we have nodes for the orders and nodes for workstations, and relate them with the started work relationship for when the processing of an order starts in that respective workstation. There's a disadvantage here, and we kind of lose the bit of notion of a network between all orders and workstations that we had before in our previous image. But there's also something like this possibility. The advantage here is that we keep the network structure, and basically we create nodes for orders and nodes for workstations, and we can create a projected path for an order when it enters the system, and we update the respective relationship values each time a given order leaves processing on a workstation. So imagine this order comes in, we register the projected path by creating the relationships, because we already know the path it will going to take. And then each time a specific workstation is completed, we can update the relationship for that order. Note that this could be done in many different ways, and these ones I represented are just simple examples to kickstart this idea and the discussion. And the main point here is the graph theory, since this could also be implemented using relational databases. Not so simple, but still it would be possible, and the main point here is the idea. Now, let's talk about a bit about queuing theory and what's it doing here. Queuing theory studies the process of waiting in lines, as the name says, and it enables mathematical analysis of several processes. So for this, we can have, for our workshop, we could use queuing theory and data collected from those small buttons that I talked about. We could collect lots of information given by those interactions, and also applying this theory, and we could get utilization factor, which basically a percentage of a machine or a person, a worker. So if it works half the time and the other is paused because it doesn't have any work to do, it would have utilization factor of 50%. We can know the number of packages in the system, so all orders in our workstation, or in our carpentry, the number of packages in queue, by using the projected path approach, we can understand which orders haven't yet started the next workstation. So that gives us the possibility to also know this. We can, the same way, calculate the time spent in queue. So since we know the time the the order stopped working in this one and started on that one, the difference is the time spent in queue. If we collect this for all workstations and then we just do a mean, we already get a very helpful value. Can also get the time spent in system, so the time it takes from when it enters or it's registered to the time when it leaves. Service times, also very easy to calculate. It's the amount of time it takes to service it, basically, in each workstation, and you can also get the efficiency. Now, I know that this is a bit theoretical, but let's dive into what we can achieve by reusing parts of these calculations. So for this, I present you this question. So we are about to score a big deal with a major client for our carpentry, and we don't know if we can handle the request in time. Given that we already have so many orders in the shop, how can we decide if we should accept the deal or not? Given the fact that we don't have those technological machines to give us an insight. Let's do how we can do it with our simple approach. So we can use graph theory to predict delivery dates. Assuming that we know how much time each process takes and the path of processing each order needs, because we already know what's the work required for assembling a chair, and looking at workstations as if they were picking an order from the pile or the queue, doing their thing, their processing, and sending it to the next, as we can see in this image here. We can think of them as completely individual and independent nodes from each other, and implement a simple simulation. Basically, they would simply pick an order from the queue and put it in the next one after the work is done. If nothing is waiting in line, then the workstation stops and until a new one appears. This is pretty much simulating how the production line works. It can also be the starting point or the finish point of an order, of a package. We can calculate when all of our existing orders will be complete using these calculations and applying the queuing theory math. Basically, you can think of this as Google Maps showing you when you'll arrive your destination, and the problem is still modeled as a graph, and every intersection would be the workstation node, and you basically just don't see yourself moving through the road. You see yourself moving from each intersection to the next one. You could imagine this as a very similar problem. So this is where a discrete event simulation, or a DES, comes in. It's used to model and analyze systems characterized by distinct and separate events that occur at specific points in time. And we can represent our system as the set of entities that are our orders and their interactions. And these interactions can be basically our events, and the events are the orders moving from one station to the other. If you look at the image on the right, you see that we start the simulation, or we start this algorithm by getting all the events, and then we kind of loop over them, saying, okay, what's the next event? In this case, what's the next order finishing or starting a process? We make the changes to the simulation clock, and we keep iterating until all events are handled, so all orders registered have gone through their projected path. Now let's dive into a bit more specific thing, but in our carpentry workshops, events can be treated as discrete, so time ops, because events are instantaneous. We don't need to simulate the whole processing time. But let's look into an actual example. By the way, this was modeled using Neo4j Bloom because it was easy to also visualize quick things. And let's imagine we have the following state, and in red here, in red relationships, we see the ones that have already completed, and then these green ones are the path missing for the order 2, and the blue ones are the paths missing for order 1. So we have already finished polish for order 1, and we are missing varnish and assembly, and for order 2, this is the state. Basically, if we could write a simple query, we could get the next state for each order, because we already know the ones that are complete, and we know the next ones in line. And we could also get the projected path along the production line for each order. So this would give us already the events. The first 2 events is that we should start the cut, we still should start the polish, and we should start the varnish. So continuing on this simulation, as I was saying, imagine these are the first events. Order 1 is in varnish, let's suppose it has a quantity of 10, and order 2 is in Polish and has a quantity of 40. If we used queuing theory to calculate production rate, so basically the items per hour, or we use a simple approximation, because we already know our employer takes 2 hours to varnish a full table, we can use this value, and it gives us the next event. So our next event would be the minimum of these two. We have the simulation clock, can be exactly now, and then we just add the production rate times the quantity, and it should give us the future timestamp. The first one of these two, or the minimum of these two, will be the next event. Continuing with this simulation, let's imagine now we have moved through. So coming from the previous one, you see that these paths I've already completed, and we are on the last step. And what happens when more than one order is going for the same workstation? We can do the simulation the way we want to. So we can sort them by a priority field that can be a property in the order node, or we can also sort by the delivery date. For example, if an order has a smaller delivery date than the other, then it means it basically has a higher priority by default because it needs to be delivered first. There's also the calculation of the timestamp, the next timestamp, the one that I was showing before, and we can have it in the level of detail we wish. So if there is more than one server per workstation, imagine we have two people assembling chairs, or just assembling whatever they are doing. If we have more than one, then it means that we can have two orders at the same time being handled by them instead of just one node each time. And also we can account for working hours. For example, if we only work 9 to 5 on our workshop, and our timestamp calculation that we are using, for example, coming here, it's giving us that this will be at 6 p.m. Then it's 1 hour overtime, and we can just basically move it to the next day. And instead of saying, okay, this next event is at 6 p.m., it will be in fact at 10 a.m. because it's 1 hour plus in the morning. The fun part here is that we can lead the simulation the way we want to. So yeah, still continuing, and this is the final part where let's suppose all projected paths that we have in the system have been already marked as complete. So basically, an order doesn't have a projected path that isn't marked with a timestamp or whatever we decide to use. We can update the expected delivery date field with the simulation value that it outputted. The simulation ends when there are no more orders in the queue, and we have traveled through the entire projected path for all of them. So looking at this example, we see that there are no more orders, no more relationships that they haven't gotten traversed. So this shouldn't keep working. Now let's dive into a bit of more discussion part and why we're not using AI or machine learning, or why we don't need to use it all the time. And the main part here is that the DES, so the discrete event simulation, as a graph, as we saw it now, it's very easy to set up. So firstly, we could also implement a concurrent version using threads or processes. What I mean by this is that since we are thinking of workstations as independent nodes, we can also look at them as independent processes. we could eventually implement our simulation using instead of a single query loop, we could have these processes interacting with them and passing in messages as if they were the actual orders. Another plus point for this approach is that it adapts to the current production line state. What I mean by this is that, as you saw, it always gets the query. It always uses the query to get the next events and the projected path for the orders inside the production line. And for example, if we run this every hour, then it means that orders that were completed in the meantime or orders that were registered will be accounted for in that simulation. And we can have almost like a almost real-time simulation. And when will this order be complete, because it's always changing given others are leaving or entering. And the last part is that you just need to write code in the language of your preference. You can implement a simulation like this in any language, and also in any database. It could be Neo4j for the simple of use. And if, for example, as I showed you, if you use Neo4j, Bloom, and Aura, you almost don't need anything. You just need to get data there, and you don't need to implement a front end or something like that, because you already have all the visualization tools. While if we are going to use a machine learning approach, it requires lots of data to train the model. So we have kind of a tough point to start. We kind of need to collect lots of data from our workshop first, and then train the model, and then put it in production per se, while something as this simulation could go from the first day and no previous data required. Also, because these simulations are mostly deterministic, it's also a plus, because predicting or making tables or shares are also mostly deterministic. Obviously, sometimes there are things that come up and we need to delay or something like that. But if we are running the simulation every X time, then we can overcome that pretty easily. Also, just to finish, for machine learning, there's still a learning curve to it, and a whole new problems like ML ops that probably most of you have already heard. And it's not too much fun if you don't really enjoy it. This is, even though lots of tools help you with AI and ML algorithms nowadays, like for example Neo4j, Aura, and DS, but still I believe that DES, the Discrete Event Simulation, is a good approach to start. Also, obviously, this is just a shallow comparison, and I kind of missed the data to actually compare both approaches in terms of proper results. But still, I was able to implement a system very similar to this one I described here in a production factory, and the results were the following we are seeing in this slide here. So these are the results mostly for 1 year, but it has been running ever since. And after 1 year, packages delivered on time increased about 40%, which is great, because everyone now knew exactly when they could give an estimate to the client, because they had sometimes dozens, or I won't say hundreds, but dozens of orders inside the production line, and they could have a proper view of their system. Also, the overall equipment efficiency remained stable across the year. What I mean by this is that doesn't necessarily mean requires to be a machine, but can be a worker or an employer, and it basically means that they kept with a high performance per se, in the terms of of a percentage of the time they should be working and the production rate expected. And also, we identified production patterns and bottlenecks. If you look at these images here, these are the workstations, and in the y-axis, we have in green ones, we have the number of orders in the queue for those specific workstations, and you can clearly see that the first 3 or 4 workstations are the ones that there are more and more orders piling up before they move on to the final ones. This is also matched with this little plot here. It's a heat map, and we can see that these same workstations here are the ones below. So it matches that most of them, or most of the orders, need to go through these workstations. So if we wanted to reduce the number of the piles here, then we probably should increase the number of workers or the number of machines in these respective workstations, because okay, they pile up, but there's a reason for it, because every order, or almost every order, goes through it. And I think that's it. That's mostly it. And there were lots of topics to dive deeper in, some specific slides also, but I tried to keep this as broad as possible so that everyone could understand the problem from top to bottom. Now I hope to have inspired all of you to look at problems in a different way, as not everything needs to be improved by super effective machines replacing humans, or achieve good prediction results only with AI, because sometimes a simple approach is also very, very valid. So yeah, thank you for listening.